So these were the first computers to run a weather forecast in the UK, down at the Met Office, and they were designed, oh, let's see, Dave. Designed by you busy bees up here in Manchester, right? So you're part of the heritage of this supercomputing. Yeah, this is what I was just talking about. This green dotted line, if you can see it across the top, this is the best-in-class traditional weather model. This is year across the bottom and quality of forecast up the y-axis, and each black dot is an AI model published in a paper. You can see here, there's this sort of point of inflection where these models, like I said, at least become comparable. Like I just said, look, we can talk about whether they're better or worse. That's not very interesting. The point I think is much more interesting is you can do things with these models that are just completely inconceivable traditional models. So yeah, I mean, it takes maybe, let's say, less than a minute to run one of these models as opposed to an hour to run a traditional model on a supercomputer. So this opens up a whole new realm of possibilities. Okay, so that finally brings me to Earth 2, where I work. So in a nutshell, in Earth 2, we make open science and open software to enable the weather and climate community to leverage AI and accelerated computing in their tasks. We don't issue forecasts, we don't run platforms, we don't run services. It's really important to make that clear. So we don't compete with our customers, our developers. I'm here to enable downstream developers to use these technologies. And you know, there's a few different ways we do that. These icons are different models that we've published, which I'll go through in a second. But importantly, we also put a lot of effort into doing, in inverted commas, the boring stuff. So documentation, training courses, workbooks. We publish all our code on GitHub. We build on PyTorch. We publish our models on Hugging Face. So really, my job is to make it as easy as possible for people to pick these technologies up. So just after Christmas, we sort of published a suite of models. Some of them have been around for a while, but some of them are new. And we think now that these models cover a lot of the different tasks that you need to do weather forecasting. So there are different types of weather forecasting and different jobs to do there. Okay, so here's the first model. So kind of bread and butter stuff. You're I guess, like bog standard, next 2 weeks, what's the weather going to be like? So we've got a model called Atlas. So this publishes out for 15 days. As I said, there's lots of different ways to measure scale. Look, we think this one's pretty good. But the point here is you can run it in a minute and a half on a laptop. So, I mean, this is absolutely inconceivable 5 years ago. This was not obvious that this was going to happen. And it predicts lots of different types of weather. So for people who like architectures, here's the architecture. So this is based on a diffusion transformer architecture. One of the interesting things about this is, if people have heard of the bitter lesson, you know, there's a question, this is a very new model. Part of the debate around this model is this the bitter lesson for weather? So the bitter lesson says something along the lines of that, you know, it's tempting as a domain expert to come to these problems with all your domain knowledge and use that domain knowledge to try and construct and inform the way you design your machine learning algorithm, your AI algorithm, to be as effective as possible. And time again, the bitter lesson is that actually it turns out if you just use standard architectures and brute force it, you often get a better answer. So, you know, as a domain expert, I can taste the bitterness there. But this diffusion transformer architecture is very similar to the architecture that's used in a lot of other models like large language models and that sort of thing. I should say, we do have some predecessor models for this that are very good, that are informed by you know, spherical neuroharmonic operators and this kind of thing. But currently this one's winning the race. So this passes the vibe check. This is observations on the left and the model on the right. But, you know, okay, so what? So if you're a weather forecaster, that's kind of interesting, but if you're not, like, what can you do? This is one of the things that you can do that just isn't possible before. As I said, this is the kind of canonical example of a chaotic system. So one of the ways you sample chaotic uncertainty is to run an ensemble. You run the same forecast multiple times, and you get slightly different answers from your chaotic system. So here's some hurricane tracks. With this traditional supercomputer, where it takes an hour to run an ensemble forecast, you might do it 30 times. You can crank out 10,000 ensemble members with a machine learning forecast, which lets you sample these extreme events and really quantify the uncertainty in a way that's just not possible. So this is some work we did with AXA, the insurance company, to look at quantifying historical hurricane risk. You can also use it to generate fine structure from coarse structure to do downscaling. So this is an example of taking a coarse field over the continental United States. Now this can be generated with a traditional model or an AI model. and generating that fine scale structure from the coarse scale structure. And this uses, this is a bitter lesson kind of thing as well, this uses a diffusion architecture. So for image generation, the way diffusion architectures work is you train the model by taking an image and iteratively adding noise to it, and training a model to remove iteratively that noise. It's kind of amazing to me that this works conceptually, but it does, right? And so just in the same way you can do this for a particular, generating a particular image, you can also do it for weather. And, I'm not going to go through this slide in detail, but you can also take this approach and turn it into what we call a nowcast. So instead of training the model to generate structure, we're working with Dave and you guys at Manchester to apply some of these techniques to air quality predictions. So this embedded box in the top left is where we're taking these diffusion techniques and we're running it on top of our coarse resolution chemistry model to create ultra high resolution air quality forecasts over the UK. Okay, so we've also just published a model that runs directly from observations rather than training on some kind of physical training data set. This is a very high resolution model that's trained on satellite data. So it's essentially doing an impression of satellite data. And we think for the next kind of 2 hours at a 10-minute resolution, we think this is the first time an AI model's beaten an explicit physical model on those short time resolutions. And again, you'll see here that this runs in less than a minute on a laptop. And here's some vibes checks for you. I actually pulled these out somebody else's presentation and I couldn't figure out which one was the obs and which one's the prediction, so I think that tells its own story, right? There's another one. So I'd like to make something clear actually before we talk about dogs. I'd like to make something clear. When I say that this was the preserver of nation state, what I'm not saying is that we don't need the nation state to do weather forecasting in any way. What I'm saying is that bespoke applications that are tailored to you, what you're trying to do in your decisions are now possible. So this is what I was just talking about. This is an example of various progressive models creating a solar PV nowcast. This is with an energy company in China. Yeah, and we've got a bleeding edge model application around what if generation of weather. So this is what if there was a picture of a golden retriever dog wearing a blue checker beret and a red dotted turtleneck. Right, this picture never existed before, but as you know, you're able to create images like this. So we've taken a similar approach to weather. And we've said, what if I had a tropical cyclone at this location, and what if that happened in this specific climate, which I've defined, on this specific day of the year at this time of day? And what's amazing to me is, in the time that I waffle about this video, it can go away and generate a global, very high resolution animated field of such a weather event that's never existed before, but is statistically representative of the climate it was trained on. So this model can be trained on petabytes and petabytes of data, and in a couple of gigabytes of model weight, it can recreate statistically equivalent data of the climate that it was trained on. So there you go, there's a tropical cyclone that's never been seen before. Okay, I just wanted to sort of finish off with another video, which is about...
Total worldwide wind energy capacity currently exceeds 750 gigawatts, and is growing faster than ever, with an additional 650 gigawatts to be added in the next 5 years. For companies like Siemens Gamesa Renewable Energy, optimizing the configuration of each new wind farm is critical for getting the most out of their investment and reducing costs for consumers. When designing a wind farm, it's critical to place each turbine so as to minimize the effects the turbines have on each other due to the wake that they create. Accurately modeling the wake requires high-resolution, high-fidelity simulation data that is specific to that wind farm, such as the geographic location and the terrain. The gold standard for generating this data is the large eddy simulation shown here. But to run just one iteration for a single turbine can take 40 days on a 100-core CPU. And with so many iterations needed to develop an accurate model for a specific site, using CPUs is impractical. Using NVIDIA Modulus and NVIDIA Omniverse, Siemens Gamesa has been able to reduce that 40 days to just 15 minutes, approximately 4,000 times faster. This is accomplished by running the model at a lower resolution, and then, with a PhysicsML model trained using Modulus, to enhance or super resolve the data, and the results are functionally equivalent to having run the model at full resolution. Let's take a look at the same data presented in a way that clearly highlights the coarseness of the low-resolution simulation. Here, they look like pixelated blobs. In the super resolved flow field, you can see the finer vortex structures. Now that we have the simulation data, we can build an accurate weight model for the site and optimize the placement of each turbine. Thousands of iterations, accelerated by NVIDIA GPUs, are run as part of the optimization to achieve the maximum power output for each farm while minimizing the cost. And the impact is huge. When using NVIDIA Modulus and
Okay, I'll just kill it there. So you get the idea. This is a slightly different example of the same thing, right? Which is about using machine learning, AI, to emulate and accelerate what would be a prohibitively expensive thing to do, especially when they're doing that iteration at the end. You imagine each iteration is essentially a different run. I just wanted to talk nuts and bolts just before I finish, which is, I mean, this is, we publish GitHub repos. There's one for doing improvements called Earth 2 Studio. I encourage you to go and look if you're interested. There's a whole bunch of different models that you can apply here. I just want to point out these orange models are not NVIDIA models. I'm very proud of our models. I'm not saying that they're the only models and you have to use them. These are models from people at Microsoft and Google and ECMWF for people who know who that is. But I mean, this is absolutely crazy that in 4 lines of Python code, you can run a forecast that used to be millions of lines of Fortran and prohibitive. So yeah, here's some QR codes to finish. There's a library for inference, there's a library for training, there's a training course, and there's a tech blog with lots of examples of how we've used this with customers. So thanks very much, looking forward to the questions.